everyone, today we're doing lesson 5.4 part 1 of the Fundamental Theorem of Calculus. Notice that you can't say fundamental without saying fun. So a lot of times we call this the FTC, the Fundamental Theorem of Calculus, but I like to call it the Fun TC. So let's go ahead and get started. So let's first read through the first part of the fundamental theorem. So it says, if f is continuous on a closed interval from a to b, then the function big f of x is equal to the integral from a to x of f of t dt. Let's pause there. What is this saying? Because this is the first time that we've had a function defined as an integral. So here I have a graph of f of t. Notice that it's a positive function, but that won't matter. It was just for ease of a picture so we could kind of visualize what's going on here. So let's take a look at the integral. So the integral is from a to x. So I'm starting at a and I'm going to x, right? And I know the integral stands for the area above the curve minus the area below the curve. Since I have no area below the curve, I'm just going to go ahead and fill in the integral from a to x of f of t dt would be equal to this blue shaded region right here. So this would be big F of x would be equal to whatever this area was right here, the integral from a to x. So long as f is continuous on the interval from a to b, and I have this function, big F of x, that is equal to the area under the curve from a to x, where x could be any point within this region from a to b. They're saying big F of x has a derivative at every point x within the closed interval from a to b. And not only does it have a derivative, but the derivative, f prime of x, is equal to f of x. So big F prime of x is equal to f of x. And this is just a bunch of different notations here. So big F prime of x could be written as d big F of x, which is taking the derivative of the integral. And when I take the derivative of the integral, hopefully what the connections we've been making over the last 3 sections have helped us see that when I take a derivative of an integral, these are inverse operations. I didn't mean to write that. I wanted to highlight this. The derivative and the integral are inverse operations right there. Kind of like multiplication and division are inverse operations, or addition and subtraction are inverse operations. So what's happening here is, since the function is defined as an integral, when I take the derivative of that function, the integral cancels it out. And I get that big F prime of x is just equal to f of x. So there's a couple conclusions from here. One is, given that a function is continuous and differentiable, the antiderivative, going backwards, is also continuous and differentiable. And a derivative and an integral are inverse processes of one another. So let's take a look at an example. So my first example says, find dy dx for y equals the integral from 1 to x of t plus sine of t dt. So notice that I am trying to find dy dx when y is equal to an integral. So dy dx would be equal to d dx of the integral from 1 to x of t plus sine of t dt. I notice I'm taking the derivative of an integral. I notice that I have a constant right here. To a function x. And hence I can use the Fundamental Theorem of Calculus part 1. And so I notice that this is just equal to, if this is f of t, it's going to be equal to f of x, which would be x plus sine of x. And that would be it. That is using the Fundamental Theorem of Calculus part 1. Let's walk it back just a minute to my example here, and just compare my example to the definition here. So notice in my definition, my integral always starts at some constant. And it's going up to my function that is x. Okay, so I just plug this x in here for my independent variable, whatever that independent variable is. All right, let's look at another example. Here I want to evaluate d dx of the integral from negative pi to x of cosine of t dt. So I automatically notice I have a constant here. Negative pi is just a constant, and I am taking the derivative of an integral. So when I evaluate that, that would mean I take this variable and I plug it in for my independent variable for whatever function is here in my integrand. So this will be equal to cosine of x. And that is it. Let's look at the next example. Here I want to evaluate d dx of the integral of x to 6 of 1 over 1 plus m to the 4th dm. So what I'm noticing here is the derivative of the integral, but I'm also noticing that my variable is on the bottom and my constant is on the top, so it's my upper limit of integration. So I need to rewrite this. So I know that the integral from a to b of f of x dx is equal to negative integral of b to a of f of x dx. And we learned that in a previous lesson. So what I can do here is I'm going to still want to evaluate the derivative with respect to x of the negative integral from 6 to x of 1 over 1 plus m to the 4th dm. So I'm simply just rewriting the integral. So now my negative can be pulled out, because I know any constant can be pulled out of an integral. And now I can go ahead and evaluate the derivative of the integral with my constant here at the bottom. So now I know I can just take x and plug it in for my independent variable. Oops, and I'm noticing a mistake. This is dm. So make sure I have a dm, not a dx there. So I have negative 1 over 1 plus x to the 4th. And I'll write that negative 1 over 1 plus x to the 4th. So that's the fundamental theorem of calculus part 1. It just says if you're taking the derivative of an integral from a constant to a function just x, you can simply just plug in that x for your independent variable to your integrand. And again, the reason why, hold on one second, there we go, is all in the details right here in this first fundamental theorem. If a function is defined to be an integral, its derivative is simply just going to be the integrand, because those processes are undoing each other. A derivative and an integral are inverse operations per se. Let's take a look at extension though. So here I want to take the derivative with respect to x of the integral from 4 to x squared of cosine of t dt. So I notice here that I'm taking the derivative of an integral. I notice I have my constant here. Ooh, but then I notice I don't have an x up here. I have an x squared. So here what I'm going to do, it still follows the same pattern in that I'm going to be able to replace my independent variable of my integrand with that upper limit of integration since it's a function. But then what I'm going to have to do is I'm going to have to do a chain rule as well. So this is going to be equal to cosine of x squared times 2x, because 2x is the derivative of x squared with respect to x. So I'm using a chain rule here. So for my extension, if y is equal to the integral from a to h of x of f of t dt, then y prime is going to be equal to f of h of x times h prime of x. So that is an extension of the Fundamental Theorem of Calculus, part 1. And I probably should have written that right here with the space that I designed for it that I didn't use. So that's the extension rule there. So here, there's a couple that I'd like you to try on your own. What you can do is you can try these on your own, pause the video, and then once you're done, you can come back, check your answers. So pause the video now and try these two on your own. Welcome back. So we're going to go over these two problems. The first one, I want to evaluate d dp of the integral from 2 to p of 3t sine of t. So I notice derivative of integral, I notice constant, and then my upper variable. So I can use the Fundamental Theorem of Calculus part 1, and I'm going to replace all my independent variables here with p. So I have 3p times sine of p. And that's all. The next one, I have the derivative with respect to x of the integral of 3 to e to the 4x of sine cubed of 2t dt. So derivative of integral here. Then I notice constant, and then I notice, ooh, that upper limit of integration is a function that is not just a linear function. So I'm going to have to use that extension rule. So I'm going to replace my independent variable within my integrand with e to the 4x. So I'll have sine cubed of 2e to the 4x. Then I have to multiply that times the derivative of e to the 4x. And the derivative with respect to x of e to the 4x is e to the 4x times 4. So I'll have times 4 e to the 4x. And that is the first fundamental theorem of calculus, part 1. You are all set to now do page 302 and these specified numbers right here. I definitely thought that was a highlighter. How can I go back? Let's try that again. You can now do these numbers here. Don't want to cross them out. We actually want to do those. All right. Have fun.